All right, welcome back to Weekend Hustlers, everybody. It's Pavlov here, and Nikita's with me too.
Hey, everybody.
So before we get into this deep dive, we did want to ask a quick favor. We've noticed that a lot of you guys listening, I think something like 75% of you haven't hit that subscribe button yet. And
yeah, it's a lot.
Yeah, so if you're enjoying these deep dives and you want to see more of this focused content, hitting that subscribe button really does help us out.
Yeah, it's the best way to support the show, and it makes sure that you never miss out on any of our future explorations.
Right. All right, so today we are taking a deep dive into a really interesting piece of technology. It's outlined in U.S. patent 12,224,005B1, and the title kind of gives you a hint of what we're looking at here. Lifetime Mixed Level Non-Volatile Memory System.
Yeah, this is a real deep dive. We're going to be looking at the patent document itself. So this is going to be everything from the abstract, which is kind of like the summary of what the patent is all about, and then we're going to go into the detailed description. We'll even be looking at the claims, which are very specific aspects that the inventors are laying claim to.
Right. So our mission today is to really unpack the core ideas behind this patent. We want to understand how this invention aims to make something that's really important in modern electronics. Non-volatile memory. We want to see how it makes these memory systems last longer, be more reliable. Think about all the places where you encounter this kind of memory. Your phone, your laptop, those super fast SSDs. This patent kind of gives us a glimpse into how we can potentially make these things more durable.
Yeah, and as the name implies, it's tackling this problem by looking at this mixed level memory system. So we're going to really look at the clever ways that this patent proposes that different types of memory can be integrated and managed within a single device, all with the goal of making it last longer.
Okay, so let's start right at the beginning. Let's go to the abstract. What does the patent kind of put out there as its big idea, the big picture in the summary?
Right. So the abstract basically outlines this invention for storing data in non-volatile memory. And the central player is this thing called a controller, right? And this controller is like the brain, the manager, if you will. It's in charge of all these different memory cells, which is where data actually gets stored. But here's where it gets a little nuanced. They make this distinction between the physical memory cells, those are the actual little spots where data is stored, and logical address ranges.
So like the address that my computer thinks it's using versus where it actually is.
Right, exactly. Think of it this way. The logical address is like the street address that your computer uses to find the data. But the physical address is the actual room in the memory building where that data is actually stored, right? So the controller is smart. It can write information to multiple physical memory cells that all correspond back to that single logical address.
So it can be in multiple places at the same time.
Kind of. It's all about flexibility and how the data is managed. But here's where it gets really cool. This controller, this smart manager, can run a test. It's called a data integrity test on an initial group of these physical memory cells. It's like a little health check for that part of the memory. And if this test comes back and says, uh-oh, something's not right here.
If it fails.
Exactly. If it fails, if it's hey, this part of the memory might be getting a little iffy, the controller can then write some or even all of that information to a second group of physical memory cells. And remember, these are all within the same non-volatile memory chip. But here's the crucial part. The controller updates its little map. So that original logical address, that street address your computer is using, is now pointing to this new, healthier backup location.
Ah, okay. So it's like having a backup, like a spare room in the memory building itself, right?
Yeah.
If one spot starts to get run down, the system can just kind of quietly move things around and update its address. Nobody even notices.
Right. Exactly. It's all about proactively identifying potential issues and being smart about how you deal with them. Instead of waiting for a catastrophic failure, it's nope, let's move that data to a safer spot and just keep things running smoothly.
I like it. Okay, so that's the big idea. Now, let's dig into the why behind this whole invention. In the background section of the patent, what problems with existing non-volatile memory does it highlight as the motivation for coming up with this new approach?
Right. So the patent starts off by kind of emphasizing just how vital non-volatile memory is in pretty much everything we do these days. They're the things that hold on to our data even when the power is off. They're in our phones, our laptops, pretty much every gadget you can think of. But then the patent goes on to point out that, well, all these traditional forms of non-volatile memory, and they list quite a few things like hard disk drives, phase change memory, resistive RAM, magnetoresistive RAM, and then, of course, all the different flavors of flash memory, like NAND, they all have their limitations.
Right, nothing's perfect.
Right. Right. Every technology has got its trade-offs. You can't have it all, at least not yet. So the patent really zeroes in on two main needs. Improving the lifespan of these memory systems, how long they can keep working reliably, and their reliability itself, making sure that the data you store actually stays intact and doesn't get corrupted. And this is increasingly important, right? We're storing more and more data than ever before. We expect our devices to just work, to remember everything perfectly.
And I imagine as memory cells get smaller and smaller,
Yeah.
To cram more storage into the same space, I bet those reliability challenges become even more of a headache.
Oh, absolutely. The patent specifically dives into NAND flash, which is one of the most common types of non-volatile memory we see everywhere. And it highlights this inherent trade-off between two main flavors of NAND, single-level cell, or SLC, and multi-level cell, or MLC.
Okay, break those down for me. What's the key difference between those two, and why would you use one over the other?
Right, so SLC NAND, it's designed to store just one bit of data per memory cell. This makes it super fast, both for reading and writing. And it's also got this really high endurance. It can handle way more write erase cycles before it starts to kind of wear out. But, there's a trade-off, right? Because it only stores 1 bit per cell, it's also generally more expensive. And it's got lower density, meaning you need more physical space to store the same amount of data compared to some of the other options.
So it's like a Ferrari, right?
Yeah.
Fast, durable, but not super practical for hauling groceries.
That's a great analogy. Now, MLC NAND, it's more like your minivan. It's designed to store multiple bits of data per cell. This means you can cram way more data into the same physical space, higher density. And because of that, it's usually cheaper to manufacture, but the trade-off is that it's not as durable. It can't handle as many write erase cycles as that speedy SLC, and the write speeds are usually a bit slower too.
So it's like the classic engineering problem, right? You can either optimize for performance and longevity, like with the SLC Ferrari, or you can go for capacity and cost, like with the MLC minivan. You can't really have the best of both worlds, at least not with just one type.
Exactly. And this is the core problem that this patent is trying to tackle with its solution, which is, as we've said, this mixed level memory system.
Okay. So how does it propose to bring those two worlds together? How do you combine the advantages of the Ferrari and the minivan in one system?
Right. So the central idea is to create a storage system that uses a mix of different types of non-volatile memory. Now, the patent mentions that various combinations are possible, but the main one they focus on is using both MLC and SLC NAND flashed together.
So it's not about picking one over the other. It's about teaming them up.
Right. Exactly. You want to leverage the strengths of each one. So you use the high density and lower cost of that MLC. Remember, that's your minivan, good for bulk storage for the majority of your data. That's where you're storing most of your files and applications and all that stuff. But then you sprinkle in some of that high endurance, more reliable SLC, that's your Ferrari, for the really important data. Or as we saw in the abstract, as a kind of reserve, a backup for when parts of that main MLC storage start to show signs of wear and tear.
That makes a lot of sense. Use the minivan for the everyday stuff, but keep the Ferrari in the garage for those special occasions, or when the minivan starts to sputter.
Exactly. It's all about being strategic. And the key to making all of this work, the brains of the operation, is this thing called the controller. That's what the patent focuses on.
Yeah.
It's this special controller that's designed to intelligently manage the reading and writing of data across all these different memory types. It has to decide where to put things initially and then how to react if one of those memory types starts to act up.
Got it. So the controller is like the traffic cop, directing the data to the right place at the right time.
Exactly. Now, the patent has some really helpful diagrams. Let's take a look at figure 1, which I think shows the main components of the whole system.
Okay, yeah, let's pull that up. What should we be focusing on in this diagram?
Right. So figure 1 is kind of a high-level overview of the system. They label it 10, this whole system. And you've got your processor, which is, the main brain of the device. That's labeled 12. Now, this processor talks to a really crucial component, the device controller, which is labeled 14. And this is the conductor of the memory orchestra.
So that's the one that's deciding where everything goes?
Exactly. Now, the diagram also shows DRAM, that's labeled 20, and that's a type of super fast temporary memory. Think of it as a super speedy waiting area for the data before it gets written to the slower non-volatile memory. And then, kind of interestingly, we also see disks, that's labeled 24, and the patent kind of notes that these could be your traditional spinning hard drives or even optical disks, which I thought was kind of cool. Yeah. It means this whole mixed level flash system could potentially be part of a much larger storage setup working alongside those older types of storage.
Interesting, yeah, like a hybrid approach.
Yeah.
But the real stars of the show here are the MLC flash, that's 26, and the SLC flash, that's 28, right? Those are the two types of memory that the controller is juggling.
Exactly. And then you've got your I/O interfaces labeled 16 and 18, which are basically how the whole system talks to the outside world. But for our purposes, the device controller and how it manages all that data between the DRAM, the MLC flash, and the SLC flash, that's the heart of this diagram.
Okay, so the controller is like the air traffic control tower, making sure everything lands safely and in the right spot.
I like that. Now let's look closer at that data integrity and remapping process. Remember we talked about that? Figures 2A and 2B give us a more detailed look at how that actually works.
Yeah, let's pull those up. So 2A shows these logical address ranges, R0, R1, R2, all the way up to Rn. And they're mapped to these physical addresses in the MLC flash module. It's like a table showing you where everything lives, right?
Right, exactly. So you can see that logical address R2 is initially pointing to MLC block 2, but then there's that arrow that says failed data integrity test. That's pointing right at that mapping, meaning, the system has detected a potential problem with that MLC block.
It's like the controller saying, wait a minute, something's not right with this storage unit. We need to move this stuff.
Exactly. Then figure 2B shows what happens next. All those logical addresses, R0 through Rn, are still there. But now, the mapping for R2 has changed. There's an arrow that says remapping to SLC flash module, and it shows that R2 is now pointing to a block in the SLC flash module. In this case, it's SLC block 0.
So it's like rerouting traffic, right? You hit a roadblock, so you take a detour. But in this case, the detour is to a much more reliable, high-performance road.
Exactly. This remapping process is how the system can essentially, dodge those potential potholes in the MLC and keep the data safe and sound in that more reliable SLC flash.
Okay, so that's the high-level view of the remapping process. Now, let's get into the nitty-gritty of how data is actually written to this mixed-level memory system. Figures 3A and 3B, they give us a flow chart. It's kind of a step-by-step recipe for how the write operation happens. Can you walk us through that process?
Right. So this flowchart starts at step 100, which just says begin, right?
Yeah.
That's always a good place to start. And it outlines the entire sequence of actions that happen when you want to write data to this non-volatile memory. First, at step 102, the system reads the data that needs to be written, they call it a data quantum, in the pattern from the DRAM into the device controller's internal memory. Remember, the DRAM is like that super fast temporary holding area.
It's like the loading dock, right, where the data is waiting to be processed.
Exactly. Then, at step 104, the system looks at the logical address where this data needs to go. What's the street address for this data? And based on its internal map, it figures out the corresponding physical address in the NAND flash. And initially, the assumption is that this is going to be an MLC block.
So it's like the controller's looking up the address in its map book.
Exactly. Now, here's a little quirk about NAND flash memory. You usually have to erase a block before you can write new data to it. It's like clearing the whiteboard before you can write something new. So at step 106, the system might need to combine the existing data that's already in that NAND flash block with the new data that's coming in. This is because NAND flash is typically written in smaller chunks called pages within a larger block, and you might not always be overwriting the entire block at once. So you have to kind of merge the old and the new.
So it's like adding a new paragraph to an existing document. You don't want to just erase the whole thing and start over.
Exactly. Then at step 108, the system actually does the erase operation. It wipes that target physical address range in the NAND flash clean. It's like hitting the clear all button.
All right, so the whiteboard's clean. What happens next?
Now at step 110, the combined data, that mix of old and new, is finally written to that erased physical address range in the NAND flash. And remember, we're still assuming this is in an MLC block at this point.
Okay, so the writing has happened. Is that the end of the story?
Almost, but not quite. The system is smart. It wants to make sure that everything went as planned. So at step 112, it reads back the data from that NAND flash location that it just wrote to. It's like double checking its work.
Like hitting save and then opening the file back up to make sure it's all there.
Exactly. Then at step 114, there's a comparison. The system compares the data that was originally meant to be written with what it just read back from the NAND flash. And then step 116, there's a decision point. Did it match? Was the write successful?
So it's like a little pop quiz for the memory.
Right. And if there's a match that's the yes path, then great. Everything worked perfectly, the write was successful, and we move on to step 118. But if there's no match, if something seems off, that's where things get interesting. That's where we go down the no path, and the remapping to the SLC comes into play.
Okay, so if the memory fails the pop quiz, the controller steps in and says, all right, time for plan B. Let's move this to a more reliable spot.
Exactly. So if there's no match suggesting that something might be wrong with that MLC block, the system jumps to step 120. It starts looking for an available unused block in the SLC flash, that more reliable Ferrari section of the memory. And at step 122, it checks, is there actually an available SLC block? If there isn't, that's the no path, then, we might have a problem. You can't remap if you've run out of that spare high-endurance memory. That's step 124.
Yeah, even Ferrari has limited trunk space.
Right. But assuming there is an available SLC block that's the yes path at step 122, then at step 126, the system does the remapping. It updates its internal map so that logical address that was pointing to the potentially faulty MLC block is now pointing to this fresh new SLC block. And then the whole process kind of loops back to step 110, where the data is now written to that newly mapped SLC location.
So it's like it tries the minivan first, but if that doesn't work, it seamlessly switches over to the Ferrari.
It means constantly monitoring and making sure your data is safe and sound.
Very cool. Okay, let's move on to figure 4, which gives us a kind of conceptual view of how the memory is organized within the whole system.
Right, so figure 4 shows us this like high-level architecture of the memory system itself. They label it 50, and you can see these blocks that represent both the MLC flash labeled 68A and 60B and the SLC flash labeled 62A and 62B. It really shows you how those two types of memory are coexisting within the same device.
And we see multiple blocks of each type. Does that mean like the proportion of MLC to SLC could be different depending on what the memory is being used for?
Absolutely. That's a great observation. The diagram is just meant to be illustrative, right? In a real device, the actual ratio of MLC to SLC could be tweaked based on all sorts of factors. The cost, the performance needs, how much endurance you need. The key takeaway is that both types are there, working together.
Got it. Now, there's this thing labeled FTL, the flash translation layer. We've kind of touched on this before, but can you remind us what that does?
Oh, yeah, the FTL. It's so important. It's like the unsung hero of solid-state storage. Basically, it's a layer of software that handles all the low-level management of the flash memory. Its main job is to translate between the logical addresses that your computer's operating system uses and the actual physical addresses on the NAND flash chips. It's like a language interpreter.
It's like the universal translator for the memory world.
Exactly. But it does way more than just address translation. It also does this thing called wear leveling, which is all about making sure that the write and erase cycles are evenly distributed across all the memory blocks. This prevents any one block from being worn out too quickly, which helps to extend the overall lifespan of the whole memory.
It's like rotating the tires on your car, right? You want to make sure they wear down evenly.
Exactly. And very importantly for our discussion today, the FTL would also be responsible for implementing that remapping process we talked about, shifting data from a failing MLC block to a healthy SLC block. It's all handled by the FTL. And then finally, you've got this thing labeled interface, which is just how the memory system talks to the rest of the device, taking commands from the computer and translating them into something the flash memory can understand.
Okay, so the FTL is like the conductor, the stage manager, making sure the whole memory show runs smoothly.
Right. It's the brains behind the brawn of those flash memory chips.
Awesome. All right, last but not least, let's talk about the claims section of the patent. Now, this part can get a little technical and legalistic, but based on your notes, what are some of the key things that the inventors are saying are uniquely theirs? What are they trying to protect with this patent?
Right, so the claims section is where the inventors get very specific about what they're claiming is their invention. It's all about defining the boundaries of their intellectual property. And there are several key themes that emerge from these claims related to this whole mixed-level memory system. First of all, there are claims that focus on the controller's ability to create and manage that map between the logical addresses and the physical addresses across different types of memory. Remember, we're talking about being able to point logical addresses to either MLC or SLC, and the controller being able to juggle that whole translation process.
Right, that's like the fundamental traffic cop function, right?
Yeah.
Being able to direct the data to the right type of memory.
Exactly. And then there are claims that are all about that data integrity testing process. Remember, that's where the controller checks the health of those initial memory cells, usually the MLC ones. And if the test fails, it can then write the data to a different group of cells, potentially in the SLC, and update the map accordingly. So they're claiming that whole test and remap process as their own unique innovation.
So they're saying, we came up with this smart system that can detect problems and move data around to keep things running smoothly.
Exactly. And then you've got claims that cover things like the controller keeping track of how many times data has been written to a specific physical location. This is important for wear leveling, remember, to make sure that all the memory blocks get used evenly and don't wear out prematurely. There are also claims related to how the system treats those physical memory cells differently depending on whether they're MLC or SLC. It's all about recognizing and managing the unique characteristics of each type. And then finally, there are some claims about using a time interval to determine how often data is being written to certain areas, which could be another way to optimize the performance and lifespan of the memory.
So they're basically covering all the bases, from the basic mapping and writing processes to the error detection and wear management strategies. It's all about protecting that core intelligence of the controller in this mixed level system.
Exactly. It's about claiming the novel and clever ways that this system uses both MLC and SLC to achieve that goal of longer lifespan and higher reliability.
Okay, so we've gone through a lot of technical details, but for our listeners out there, whether you're like a tech whiz or just someone who uses a smartphone every day, what's the big takeaway here? Why should they care about this patent and this technology?
What I find so exciting about this is that it shows us how engineers are constantly finding new ways to, push the limits of our technology. We're all familiar with the frustration of devices slowing down over time or even failing completely. And this patent gives us a glimpse into how we might be able to overcome some of those limitations to create more durable, more reliable devices that just work better for longer. It's like building a better engine for the digital world.
Yeah, it's like instead of just accepting that our devices have a limited lifespan, they're saying, what if we could design them to be more resilient, to adapt and keep going even when parts of them start to wear out? It's a really cool concept.
Exactly. And if this kind of technology becomes more widespread, think about the possibilities. Longer lasting SSDs, more reliable phones and tablets, just generally more robust electronics all around.
Yeah, it's like having that peace of mind, knowing that your data is safe and that your devices are going to keep working reliably for years to come. It's a very appealing idea.
Absolutely. Now, obviously, this deep dive has only scratched the surface. The world of memory technology is constantly evolving. There's always something new and exciting happening. But hopefully, this has given you a good understanding of the core ideas behind this particular invention, this lifetime mixed-level, non-volatile memory system. It's a fascinating glimpse into the future of data storage.
It really is, and it makes you wonder, doesn't it? What other creative solutions are engineers cooking up to solve the challenges we face in the tech world? What other breakthroughs might be just around the corner? We encourage you to keep exploring, keep learning, and stay curious about the amazing world of technology. Thanks for joining us on Weekend Hustlers.